Administrative. Hello, welcome back. Good morning to Chemistry 2341, Organic Chemistry. If you are live, hello. And if you are watching this on video, hello also. Anyway, so for administration this week, we are going to finish up chapter 6 this week. Okay, module 6, which is SN2 reactions. I have pared down the questions in module 6.2. You'll notice if you go to 6.2, it's down to 41 questions instead of the 60-something questions. So, and so only 2 people had put in any responses. So hopefully I didn't cut out any of the questions you answered. But so I've also gone and pared them down for chapter 7 and chapter 8 as well. So this won't happen by accident in the future. So right now the target is to have homework due on October 16th, which is Friday, by midnight. And remember, that is the reading assignment associated with it. And there's 20 points for each module, 20 points for module 6.1 and 20 points for 6.2. So don't forget that. Okay. Coming up on our schedule here, we are going to use all of this week for module 6. And then we're going to start module 7 next week, which is alkenes and alkynes. And what we'll see here is we're going to learn some stuff about SN1 and SN2 reactions, which are substitution reactions. But when we talk about module 7, we're going to talk about elimination reactions, where we're actually removing 2 things and creating a double bond. And so that's where we're going to go. And after that, we have almost all of our mechanisms, our SN1, SN2, E1, and E2 mechanisms. And at the end of next week, we're going to have a group activity to compare and contrast which is going to happen based on which reagents we're using and what the substrates are. So we should be able to determine all of that from all the next bit of information we get for the next few lectures. Okay. So let me go ahead, and are there any questions before I begin continuing on with our slides for chapter 6.2?
Yeah, I have a quick question about the homework.
Yes.
So 6.1 is due this Friday. It looked like 6.2 is due on the 19th on Top Hat. Is that correct?
Let me double check that. I was hoping to have it due the same day because I should be done with this by then. But let me see when it's, okay, saving, close. And currently, yeah, it's due on the 19th, which is Monday. Yeah, because I'm not going to finish this until probably Friday. And so that gives you the whole weekend to finish the reading. So yeah, the module 6.2 is due on Monday, the 19th. You are correct.
Okay, thank you.
Sorry, I jumped the gun there. Okay, any other questions? While you're thinking of your question or typing it into the chat room, I'm gonna go ahead and share my screen.
So just to be sure, it is supposed to be 38 for the first one and 41 for the second one?
There are 38 for the first one and 41 for the second one, yes.
Okay, thank you.
I thought I had already saved those results. Apparently I saved them in a, I have like 10 different courses on there and I saved it in the wrong course. So I had to go back and change it. So, okay, so let's go ahead and continue on. Now, the last thing we talked about last time was this weird equation. It was talking about sterics, okay? And the basic idea is that your collision rate decreases when you have big bulky things around it because the angle at which you can come into is very small, and therefore the number of times it actually hits that angle is very small. So that means big bulky things go slower, okay? Or to the point where they might not seem to react at all, okay? So what that looks like visually is something like this, okay? So in the case of this compound here, we don't know what these groups are, but we can imagine if, as they get larger, what's going to happen is that your nucleophile is only going to find one little place where it can come in and actually react. So in the first case here, if our nucleophile comes in from the front right here, and remember, this is our polarized bond, which means this carbon is the partially positive. So that's our electrophile. That's what the nucleophile is trying to hit, okay? So if it's coming in from this direction here, it's going to be deflected off because there's no way it can use its electrons to form a new bond in the same location the other group is already occupied, okay? So that means every time a molecule comes in from this direction, the reaction cannot progress, okay? So that's case number one. Case number two is where our nucleophile is coming in and it's at an angle which does not allow it to get close enough to our electrophilic center to allow it to start to form that new bond. It has to start to form that new bond in the transition state to make the reaction happen, okay? So we have a bunch of different angles that this thing can come into and still not start to form that new bond, our transition state, okay? So that's case number two. Now, case number three is where we actually get reaction to happen, okay? And so if you have like small groups, like let's call this a hydrogen and a hydrogen here, this nucleophile here can come in anywhere in this whole cone of angle here and get close enough to the backside of our electrophile to start forming that transition state, okay? So this is a case where we have very small groups there. Let's take those away and call them much bigger groups. Let's put them as methyl group, CH3, CH3, CH3 right here. And what happens in this case here is this angle that the nucleophile can come into now gets smaller because of the electron repulsion around this group here and this group here. Our attack angle starts to look like a little tiny cone. Okay, so this is the only vector which that nucleophile can come in to start forming that transition state. Okay, so that being said, this is the reason why we have the idea that as things get bulkier and bulkier, the reaction rate slows down. And we have a harder time making the reaction happen by this SN2 reaction. Remember, 2 means bimolecular, means both molecules have to be there at the same time. Okay, so now let's look at it as a function of energy, right? So this nucleophile coming in from the top here is being repelled by the electrons of the groups here, and it's being repelled by the electrons of the groups here, and it's also being repelled by the electrons there, which means that in this case, number one here, that's trying to go up here at this higher energy situation, and it doesn't have enough energy to actually try to make a transition point there. In case number two, where it's coming in this direction here, that's going to try to be going up this potential energy hill, and it won't form the transition state. Only coming in at the correct space where it's not being repelled by too many electrons here is where you can actually come and form the transition state and actually go down to products. So that's the whole concept of how sterics affect the ability to form the transition state. And if you can't form that transition state, you can't move to products, okay? So I like this visual because it kind of gives you an idea of, you can, take those words and turn them into some picture that you can use to make an argument for whether or not a nucleophile can come in and do things, okay? So sterics and electronics control all of these, right? In the case of electronics, we have a nucleophile and we have an electrophile. So we have a partially positive or a positive charge in our electrophile. We have a negative or partially negative charge in our nucleophile. So those are the electronic factors that are helping us with that SN2. Now, this is the second component, the sterics. We have to have the right angle and the right energy to get to our transition state. Okay, so let's go ahead and look at just forming that transition state, okay? So if we're just forming that transition state, we have to have our nucleophile come in opposite the other bond that we're trying to break. So this is our leaving group. This is the one that's going to leave. And if we look at our sp3 hybridized orbital, right, we have a big lobe and a small lobe. And this big lobe is where the electrons are being shared to make our bond, okay? However, this small lobe is on the opposite side, 180 degrees from where this other bond is. And that small lobe is where our nucleophile starts to donate its electrons to form a new bond. Now notice this, this transition state here, okay? We have 2 electrons trying to be shared to form a new bond, and 2 electrons trying to be shared in a breaking bond, okay? So in the transition state, really, only half of the electrons from each side are being shared at that carbon center. So there's only 8 electrons around that carbon here, but it's a really high energy state because now we have electron-electron repulsion. And that being said, that's going to force these electrons out and we form our new sigma bond here. Okay, so, but what does that also mean? Okay, that also means we had to have significant energy to overcome the electron-electron repulsion to get them that close, which means there's a huge energy barrier just to get to there. And then we had to have our leaving group willing to leave with the electrons to form that new bond. Okay. Notice the other thing that happens is we've inverted our stereocenter. See how all of these bonds are in a tetrahedral configuration like this? And at the transition state, we've gone to this trigonal planar high energy state. And then in the end, those 3 things that were attached to the carbon have inverted and like flipping an umbrella backwards. And now we have that inverted state. Okay. This always happens in an SN2 reaction. We always get this coming in with a high energy state that's very, very short-lived and then breaks to give us our new inverted stereocenter and our new sigma bond. Okay. All right. So questions about that? Okay. So the other thing we need to think about is this transition state is it's very, very short, 10 to the minus 12 seconds. Okay. So this is an instantaneous reaction. That's why we call this a concerted reaction. There is no time for anything to move around or change. Okay, we are either making and or breaking the bond at the exact same time. Nothing can rearrange, nothing can, you know, move over to something else. There's no carbocation rearrangement. None of that happens. It's just the only change you have is that inversion of stereocenter because of that little tiny, almost imaginary transition state. So if we look at it from an energy diagram perspective, we have our starting potential energy right here. We come up, we have enough energy for the nucleophile to come in and form this high energy transition state. And then this group is willing to leave with its electrons. And when it is, it comes down to products. Okay. So the first, of course, transition is our activation energy, and it can be as Gibbs free energy or enthalpy. And then the amount of energy we get out of the reaction, notice it's the products are lower than that, is our amount of free energy change or given off during the reaction, or in the case of heat, it's given off as heat. Well, so in case of enthalpy. And I like describing it with enthalpy because the idea of what's free energy, what does it look like? Well, okay, but remember in our equation that the entropy, the S, entropy, is very small, and so our Gibbs free energy is approximately equal to our change in our enthalpy. So we can look at it as heat given off. We have a change in a Gibbs free energy, a positive change in Gibbs free energy. Okay, so let's drive home that, that idea of why we have that inversion center, okay? Because we have to come in to the back side of that sp3 orbital. Remember, this is the side over here that is making that sigma bond with the leaving group here. And we have to come in and basically attack this portion of that orbital. And when it does, these electrons go away, making this side of the orbital the big side of the orbital and forming the sigma bond. And then the other side becomes the small side at the end of the reaction. So let's look at that more specifically. So at the beginning of the reaction, it looks like this. And then at the end of the reaction, we've actually changed it and it's going that way. So in this case here, this is the small side and this is the large side. And at the beginning of the reaction, this is the small side and this is the large side. Okay. Now, to do that, remember, sp3 hybridized carbon centers are trigonal. I'm sorry, tetrahedral, right? So those groups have to invert to give us that inversion of that sp3 orbital. Okay. So it happens because when we hold it in place at our transition state here, these have to move up and become trigonal planar. So they're out of the way of both of those partial sigma bonds. And then when you invert this orbital here, they also invert and give you that inversion of stereocenter. Okay, so if it starts out R, your product's going to probably end up S, unless you've changed priorities. Okay. So let's look at that again, and let's look at it from the perspective of changing the optical rotation. Okay, so in the case here, we have this group here. This is bromooctane, and the bromine's on the 2 position, meaning we have a methyl group, we have a hexyl group, and we have a hydrogen. Okay, so that creates our stereocenter, is that carbon on the 2 carbon of our bromooctane. And in this case, we can see that it's R, and you can go ahead and do that 1, 2, 3. R is clockwise, and so yes, it is R. And it happens to have a measured specific rotation of minus 34.6 degrees. Okay. Now, if we come in and attack it with a nucleophile, right here, and we go through this transition state and we have this bromine leave, we get an inversion of the stereocenter, okay? Our hydrogens here, this is still our number 1 priority, our number 3 priority, our number 2 priority, and our number 1 priority, giving it our S configuration. And notice this, our optical rotation has changed value, okay? Why has it changed value? It's gone from negative to positive, but it's not 34.6 anymore. Because we've changed the group. There's no longer a bromine on here, there's now a sulfur on here. So it is a unique compound. It is not the exact same compound, just inverted, and therefore it actually has a slightly different rotation. But in this case, it has a measured optical rotation that's positive. And assuming it was 100% optically pure and nothing else happened in the reaction. Now, in general, these inversion reactions happen at like 99% purity in inversion. Very few side reactions happen in these reactions because they happen instantaneously or concerted. Okay, so another way to look at this is to look at it in rings. And one of the reasons we like to look at it in rings is because it's a fixed position. The ring does not allow for free rotation, and therefore it's easier to see where things are going to happen, okay? So in this case here, we have our stereocenter is this carbon here. And if we measured our R and S for our 2 stereocenters on our system before we started, we'd see that the side with the methyl group is S and the side with bromine is R. Now, if we take a solvent, in this case it's acetone, we're going to go into solvents quite a bit. So start paying attention to the solvent we use. And we have this nucleophile, and we can come in and do an SN2 reaction. And we know we're going to get inversion of stereocenter because it has to go through this transition state right here, okay? So we're forming our new bond here, we're breaking our old bond here, and when we do that, that hydrogen flips from down to up. So this hydrogen is the one that is inverting. Everything else is staying exactly the same. Now, when we look at that, we can see that we have, this is still S because we haven't changed the center here. And if we went and did our priorities here, we would find that this is now an S site. It used to be an R site, but it's now an S site. So that way you don't have to redraw it. You just have to take where your priorities are. And in this case, your hydrogen's up here. So that gives you, this is your 1 priority. This is your 2 priority. This is your 3 priority. And of course, your 4 is here, which gives you your counterclockwise orientation, which gives you your S configuration. Okay, questions about substitution, SN2 reactions, and inversion? Okay, now what we're going to do is we're going to take it and look at it in the form of a Fischer projection. Okay, now it might be even easier than to do on a ring, because what you'll see is when we do these substitution and Fischer projections, what we're going to see is the inversion takes place on either side of that main long chain. Remember, when we draw Fischer configurations, you want your longest carbon chain in this vertical position. And remember that all of the substituents are coming out at us on both sides of that, and all of these are going back. So you want to remember that that's how your Fischer configuration is. Okay. So if we attack this one here, we actually have 2 possible leaving groups. We have a chloride here and a bromine here. The methyls will not substitute and the hydrogens will not substitute. So we have 2 places where our nucleophile can attack. And in this case, we're using the cyanide ion as a nucleophile. Okay. So when we do that, we know that we're going to have an attack on the backside of this bromine, which in this case is going to be in this direction. And we're going to have the cyanide attack on the backside of the chlorine, which is that direction. So notice that when we do this, the hydrogen is going to flip to where the leaving group was, and our nucleophile is going to be opposite the position of where the leaving group was. Okay, so the hydrogen is in that same location and the leaving group is behind. Okay. Now, if we did a quick identification of stereocenters, we would see that this first one right here is S and this one is R. And when we do this, we get inversion of both stereocenters to R and S. Now, in this particular case, we now have a mirror plane right here. And so this compound actually turns out to be meso. Okay, so let's do that again on a Fischer projection with just one possible thing changing. And in this case here, we have iodine acting as our nucleophile here. And we're going to be displacing this bromine. It's the only thing that we can displace. And so the iodine has to come to the back side of that, kick that out, and move this hydrogen over, giving us our iodine in the position opposite where the bromine was, and our hydrogen in the position where the leaving group was. Okay, so that makes this easy to assign where that change happened. And notice that in this case here, this carbon right here was R. We didn't react anything to that. So it's still R, it didn't change. The only center we reacted, only the center we react inverts its chirality. It inverts its chiral center. All right, questions on inversion and SN2. So I think some people will find the using of the Fischer projection much, much easier than just drawing it out. However, some people like to draw it out. So I like to show both. Okay, moving right along. Okay, so whenever we think about writing these SN2 mechanisms, what we want to do is we want to make sure that we're reacting the right thing with the right thing. Okay, so to do this, we want to put in our charges or our partial charges on either the atoms or the molecules in our system. So for example, we have, let's say we have, oh, that's not a good color. Let's change to black. All right. So if we had CH3 and an H here, okay? So if we just look at this, well, where's the polar bond, right? So we want to make sure we assign that this is our partially negative side of our bond because of the polarity of the chlorine ion, and make sure that we assign this as our partially positive side, making this carbon right here the side of attack in our SN2 reaction. Okay. Then the next thing we want to do is we want to assign also what's the Lewis acid and what's the Lewis base. So in this case, we're going to attack with neutral ammonia. Okay. So in the case of neutral ammonia, we know that this is our base because this has our partially negative charge on our system because of the lone pair. Okay. So we have our partially negative charge on this, and that is our base. Okay. Which makes it our nucleophile because it has the partial negative charge or a full negative charge. This carbon center here now is our Lewis acid or our electrophile. It's the one that has the partially positive charge. So now we always draw our electrons going from our nucleophile to our electrophile. And you always want to try to draw it opposite where the leaving group is going to leave. So when we get our final product from this reaction, we see that our nitrogen, and in this case, it's going to be positive in this intermediate we have here with our carbon here and our hydrogen here and our hydrogen there and our CH3 here, okay? So by following these steps, you should be able to think through the process of what the nucleophile is, what the electrophile is, and where the new bond is going to be. All right, questions on that, drawing that reaction mechanism? Okay. All right, so now we're going to go into the things that affect the rates of SN2. I said the whole reaction happens because of electronics and sterics, okay? So let's talk about all the different other things that might affect the rate of an SN2 reaction. The first thing we want to think about is the nature of the leaving group. Remember, the leaving group is the one that has to break its bond with the electrophilic center and take those electrons away. So that means our leaving group has electrons with it, typically a negative charge. So the idea is you want a leaving group that can easily accept negative charge. The more easily it can accept negative charge, like being a large ion or an ion that has conjugation, those are going to make the reactions go faster. Things that are very small, you know, like maybe a fluoride ion in many cases might be very bad leaving group because it's a very small ion and it can't disperse charge. So we want to look at the nature of our leaving group as one of the things. And we want to think of how stable it is as that ion. The next thing we want to think about is how reactive the nucleophile is, okay? So does it have a negative charge? Is it something that really wants to form that sigma bond, right? So the more electron density on that nucleophile, the faster it's going to react. Okay. So the next thing that happens when we start doing these reactions is we see that solvent plays a role, okay? Now solvent plays a role for a couple different reasons. In an SN2 reaction, the major effect of solvent comes from the idea of being able to stabilize the leaving group. The more easily it can stabilize the leaving group, the more it will help that reaction progress. The other thing is the more that it can dissolve or have your nucleophile be very negatively charged to let it react. So we'll look at how two different types of solvents affect the reaction rates, okay? And then the structure of the electrophile, okay? So if it's a small electrophile with a lot of negative charge, it might react very, very quickly. However, if it's a large nucleophile, maybe bulky alkyl groups, that might start slowing the reaction down, okay? So we're looking at things that are smaller or linear and are less sterically hindered will react faster. Okay, so let's look at each of these things independently and look at them as a function of maybe their acids and base strengths, okay? So the best leaving groups are those that have stable ions or molecules after they depart. For example, if you have a protonated OH, it will leave as neutral water. That makes it a great leaving group. Or if you have a big fluffy ion like iodine, That makes it a great leaving group. Okay. So the stability of the anion is related to the ease of dissociation from its conjugate acid. Imagine that when it leaves, it has to break a bond, and therefore the more acidic it is, as the conjugate acid, the less basic it is, meaning it's better to leave and stabilize that negative charge. Okay. What that means is that low pKa values or strong acids, their conjugate acids, are good leaving groups because they have that weak basic structure when they're done. High pKa values, i.e. weak acids, make poor leaving groups, and we don't see them leaving as readily. So let's kind of put that on a more of a, Bronsted-Lowry kind of scale here. So let's look at this one right here. And so we have this hydrogen sulfide ion coming in, and it's trying to react with methanol and have this OH as a leaving group. So the carbon is the electropositive side, the oxygen's the electronegative side, and we're being attacked by a negative charge on sulfur. Okay. Now, what's the pKa of that dihydrogen sulfide? So the pKa of the dihydrogen sulfide, which would be the conjugate acid here, excuse me, is about 7. Okay. So if we looked at the conjugate acid of our leaving group here, the hydroxide here, we have a pKa of 15. Okay. Now, if we convert that into, if we convert that into its pKb, which all we have to do is subtract 14 from the pKa, we would see that the pKa is 7. I'm sorry, the pKb is also 7 when you subtract 7 from that. However, the pKb of hydroxide is negative 1.7. Okay. So that being said, negative 1.7 is a stronger base than 7 for the pKb here. Okay. So even though sulfur has a really nice negative charge on it, the leaving group hydroxide is the stronger base. Therefore, the reaction will not progress. No matter how much of this you put in here, this is still too strong a base, and the back reaction will occur, and it will not form. Okay, so in this case, our driving force is to make the weaker acid or base. Just like in those previous reactions we talked about, the same thing happens in there. And we find which is the stronger or weaker leaving group by looking at comparing the basicity of the nucleophile coming in and the basicity of the leaving group leaving. Okay, so whichever one is the stronger base is going to drive the reaction in that direction. Sorry, the weaker base is going to drive it in that direction. You want the weaker base to leave. You want the stronger base to form the bond. Okay, so how do we know? Well, you can calculate these out, or we actually have some good trends that we see in this system here. Okay, so in the case of things like halogens, or things that we know are very, very strong acids, okay, so for example, iodine, bromine, chlorine, etc., we know that their acids are very, very strong. Okay, so just by analogy, that means all of these are very weak bases. Okay, so that means that if these are very strong acids, that means all of these leaving groups are very weak bases, and they should be good leaving groups. Okay, now in contrast, if we look at this next set here, all these acids on this side, the conjugate acids of these leaving groups, are all very weak acids. All of them are above 0. So the fluoride ion, the conjugate acid of that is HF, and it has a pKa of 3.2, which makes it a weaker acid than the hydronium ion here, or any of these on this side, which makes it a poorer leaving group. Now, the basicity of of the bisulfide or the cyanide or the hydroxide or the alkoxide all keep increasing, meaning they're as that acidity increases, as the pKa increases, the acidity decreases and the basicity increases. So these are becoming stronger and stronger bases as we go. And as we know, the stronger the base, the poorer the leaving group, okay? Which makes these almost never leaving groups because they are very poor leaving groups. Now, how can you trick something into being a better leaving group, okay? Well, one thing you can do, especially in the presence of something like this, if you have an alcohol and you tried to react it, its leaving group would be the hydroxide. So let's do ROH, okay? So we know this is a very bad leaving group. So we're really gonna have a very hard time displacing hydroxide on there. However, if you convert it into another group that makes it a better leaving group, you can. So what we have are what they call these tosylates or sulfonic acid derivatives. And what you do is you react your alcohol with a sulfonic acid derivative here to create a better leaving group. Okay, so it creates, this is one of the ones right here, and this is that. So we're no longer losing hydroxide as our leaving group. We're now losing this big, huge group here as our leaving group. Okay, so empirically, why is that a better leaving group? Well, it's got conjugation. It can spread that negative charge out over 3 oxygens. So it's spreading that negative charge out over 3 oxygens here, making it a better leaving group. Okay. In fact, if we look at it's related to sulfuric acid, which is right here, that's a very strong acid, which makes it a very good leaving group. So all of these are sulfuric acid derivatives. And because they can be, you can convert alcohols into these groups, you can actually remove alcohols easily after conversion to a tosylate, a mesylate, or triflate, where you wouldn't be able to remove it directly because hydroxide is such a poor leaving group. Okay, so we'll talk about that in a little bit as well. So when you see things like this toluene derivative right here, start thinking of it as a very good leaving group. Okay, questions on leaving group ability based on acid or base strength. The stronger the conjugate acid, the better the leaving group. The weaker the conjugate acid, the poorer the leaving. Okay. Now, reactivity of the nucleophile as trends in nucleophilicity. So, nucleophilicity relates to how fast the reaction progresses because it's a kinetic thing, because we are doing a concerted reaction. It happens all at one time, right? And the nucleophilicity of our nucleophile depends on several things, okay? Now, does any one thing outweigh the others? Well, you have to kind of blend things together. For example, the basicity might change in different solvents. So we have to look at all these components together to see which is going to be our driving force. So our first driving force is charge. Do we have a full negative charge or not? Or do we just have a partial negative charge, okay? Basicity, what's its likely? Basically, how strong is it as a base? Is it a weak conjugate base? Is it a strong conjugate base? These are important to know. So we think about if it's a strong conjugate acid, it's a weak base. If it's a weak conjugate acid, it'll be a strong base. Polarizability, that goes to being able to spread that charge out over a greater surface area. So for example, iodine's big and can spread that charge out and is very polarizable. You can also have things like spreading that charge. Polarizability also counts for conjugation. Like in an acetate ion, you can spread that charge out over multiple atoms, and that helps for the polarizability. Solvent will play a major role. How well it can support the nucleophile and or leaving group will affect the rate of the reaction, okay? And then the substituents on the nucleophile. Are they electron donating or electron withdrawing? Are they big and bulky or are they small? those all come into effect when we're talking about the nucleophilicity and the rate of the reaction of the system. Okay, so there's some general trends we have here, okay, so that we can follow these pretty well, okay. So the first trend we want to think about is that things, nitrogens, especially nitrogens with negative charges, are more nucleophilic than other things. So nitrogen is more nucleophilic than sulfur. Sulfur is more nucleophilic than oxygen, and oxygen can increase or decrease. I'm sorry. Each of these can increase or decrease their nucleophilicity by having charge. So our general trend would be something like, oops, right here, our nitrogen compounds with charge are stronger nucleophiles than the other atoms. But notice here in the middle here, when we get our sulfur here, our charged sulfur is about the same as our neutral nitrogen. Okay, so these are all still really good nucleophiles. And then our neutral sulfur is still more nucleophilic than our neutral oxygen systems. Okay, but now our charged oxygen is about the same as our uncharged sulfur. And then our neutral sulfur, I'm sorry, our neutral oxygen is about the same as our charged alkoxide or our alcohol. This would be the deprotonating an alcohol to make it an alkoxide. So it's an alcohol salt. And water and that alkoxide are about the same, making our alcohols the least nucleophilic of our set. So you can follow along with just that atom trend, okay? Nitrogens, sulfur, and then oxygens, anions more than the neutral compounds within each set, okay? Now, we can also look at it as a function of basicity, okay? So in that case here, our alkoxide is more basic because it was the weakest acid, conjugate acid. So this is actually the strongest base of the set. So this is nucleophile, and this is looking at just basicity. Then we have hydroxide, and then we have acetate ion. Acetate ion, because it's still charged, but it has that delocalization, making it much, much less basic than hydroxide. And then our neutral oxygen species are the least basic of the set. Okay. So within this set here, this seems to be more nucleophilic. Notice this is, this portion of this set. So within this set, we're looking at charge. Within this set, we're looking at basicity. Okay. So I said there's a couple more. So let's look at a couple other trends we'll see. Okay. So when we look at basicity, we also can look at electronegativity. Okay. So nucleophilicity decreases from left to right on the periodic table. Okay. So when we see that, fluorine has higher electronegativity than oxygen, which has a higher electronegativity than nitrogen, that has a higher electronegativity than carbon. Okay. So what that means is that we have when we have an anion on those, because they are less tightly bound. And so that makes this more reactive because it doesn't want to have an ion. This is as stable as an ion. This is fairly stable as an ion. This is not very stable as an ion. And this is really not stable as an ion. So if it's not stable, those are more reactive. They want to make those bonds more. Okay. And if you can think about it, is that this is the most electronegative atom. It wanted those electrons anyway. It doesn't want to share them. So it's less reactive to the system. This is a stable ion. We see it a lot. This is not so stable ion, and we don't see this unless we really, really try to make it. So it's very difficult to make in that respect as well. All right, so what else do we see? Okay. We can see the charge on the atom. So in general, if you're comparing two atoms like oxygen and between an oxygen that has a negative charge on it and an oxygen that doesn't have a negative charge on it, the one with the negative charge is always the stronger nucleophile. Okay, so in the case of this, we have a deprotonated alcohol or an alkoxide, and we have a protonated alcohol. Because there's already a negative charge on here, now notice we're using the same atom, they're both oxygen, so they both have the same electrophilicity. But because of the negative charge, it happens much, much faster than waiting around for the lone pairs on here to come and do the reaction and then have to lose a hydrogen to make a neutral species at the end. So charge on the atom makes sense. So typically our strong nucleophiles are the ones with negative charges that are easily obtainable. All right, so now we get to the steric effects. Okay, so if you have a big, bulky nucleophile, sometimes they never act as nucleophiles. For example, our classic case is what we call a bulky base, is what we call T-butoxide. So this is the T-butyl alcohol, OH. We've removed a proton here and given it a negative charge, okay? Now, it has a negative charge. It wants to be a nucleophile, but it's so big, it can't get close enough to interact with the other side, the back side of that orbital, so it doesn't react as a nucleophile. It's just too big, okay? So the steric effect is inhibiting that from working. However, if you only have methanol right here, it is nice and small and can go in and create that reaction. So when we do our next chapter, we're going to see that this base right here, it's a base because it's deprotonated, can't act as a nucleophile because it's too big and bulky. Okay. So the next thing we need to think about is the steric hindrance doesn't really affect the basicity that much. All the alcohols are approximately the same, okay? But it does not allow the electrons from that negative charge to get close enough to form that double bond, to form that new sigma bond, okay? And because of this, we end up doing an elimination reaction instead. And so we'll actually talk about that in the next chapter. And we end up using this particular very sterically hindered bases and nucleophiles. We'll actually do a different reaction called an elimination reaction. Okay. Therefore, when we're talking about our species here, our nucleophile has to be small enough to be able to come in and make that transition state. Okay. So, but if it's not small enough, then it's going to act as a base and actually go through a different reaction mechanism. I'm going to change colors. All right, so the next, let's see. Oh, we got 2 minutes. Yeah, let me do polarizability. Okay, so I said polarizability is one of the things we have to look for. And if you can think about it, the larger the species is, the more polarizable it is, the more you can hug a little bit of electron density to either side of the material. So just within the halogens, even though fluoride is more electrophilic than iodine, iodine is much, much bigger. And because it's much, much bigger, it is a very good nucleophile because it can be polarized, and therefore it makes it a better. And so notice the trend here. In a particular solvent right here, it will completely trend with the size of the charge, okay? So this is the biggest charge and this is the smallest charge here. Notice that this only happens in polar protic solvents, okay? Now, the reason I say that, we're gonna talk about solvents again, but in polar protic solvents, it's because they can be partially protonated and you have to think about acid-base strength. But let's talk about polarizing here. So if we go down the one of the rows on the periodic table, we have oxygen, sulfur, and selenium, okay? So oxygen's the smallest. They all have about the same electrophilicity. However, oxygen is the smallest of them. Sulfur gets bigger, and that makes it a better nucleophile because it's bigger and polarizable. Selenium's even bigger than that, and it is the most nucleophilic of that group of elements as we go down. Okay, and likewise, we have sulfur and phosphorus are down 1 as well, and sulfur is a little bit smaller than phosphorus, and phosphorus is bigger than sulfur, and therefore is polarizable, and we can use it. And both of these actually have lone pairs on them that are part of where the nucleophilic, those are the electrons that are going to reach out and be nucleophilic. Okay, so that brings us right about 1050, and so we'll continue on all the different factors that are related to the nucleophilicity. At the end of this, what we're going to do is we're going to tabulate all the different nucleophiles and kind of rack and stack them, and then you can see which factors make them better or worse nucleophiles, and which factors make them better or worse bases. Okay. Good point. Early voting started yesterday. There is one location on campus, and it's early voting through the middle of next week. So go ahead and remember to get out there and vote and have your voice heard. Thank you for the reminder. All right. And then if you can't do that, November 3rd. All right. All right. Thank you very much. Stay behind if you have a question. I'm going to stop recording.